Hello everyone, I'm Nour Chahrour, a PhD student at University Grenoble Alpes. I'm working on the topic related to time-dependent deterioration and maintenance modeling of protection structures located in mountains to resist natural risks. Starting by the general context, torrential watersheds are subjected to different types of natural hazards such as floods, debris flows, and landslides. These phenomena generate danger and put people and assets at risk. Structural protection measures, such as check dams, retention dams, and levees, are constructed in watersheds aiming to resist natural hazards and thus to protect people and properties. In our study, we focus only on check dams, which are usually located in series along the flow channel of the watershed, constituting an interdependent protection system. Check dams are civil engineering structures that aim to achieve several functions, such as stabilizing the bed and centering the flow by their hydraulic weirs, thus preventing longitudinal and lateral erosions. It's true that these dams are efficient in reducing the risk induced by natural phenomena. However, over their lifetime period, they deteriorate and they may be subjected to failure modes that can be either structural or functional. Structural failures exist when there is a loss in the internal or external stabilities of the dam. On the other hand, functional failures are related to the performance level of the dam. At some point, the dam will no more be able to achieve its required functions. Two examples of this type of failure are the phenomena of local scoring, characterized by the removal of soil under the foundation of the dam caused by high-intensity water flows, and the phenomena of lateral bypass, in which the flow bypassed the wings of the dam, thus eroding the banks. In this study, we aim to assess the dynamic efficacy of the dams while being subjected to flood events, taking into consideration the three components of efficacy: structural efficacy, representing the level of stability of the structure; functional efficacy, corresponding to the level of performance of the dam; and 3, economic efficacy, in which the cost of maintenance or construction of these structures should be compared with the level of protection they provide. In order for the dams to preserve a good efficacy level, they should be regularly inspected and maintained. Based on the detected state of the system, the choice of maintenance could be either preventive, applied prior to the complete failure of the dam, or corrective, applied after the total failure of the dam, in which the dam is replaced by a new one. Such interventions cost much, so it's essential to know how often should we inspect, when should we apply maintenance, and which maintenance operation to be applied. Hence, our objectives are: 1. To figure out how functional failure can trigger a structural failure, and in this study we focus on the phenomena of scoring and how it triggers loss in external stability of the dam. 2. To develop a physics-based model that allows modeling the deterioration or the time-dependent state evolution of a check dam by defining degradation states of the dam and estimating the transition times linking between those states. 3. To develop a decision-aiding model that uses condition-based maintenance policy in which each state will be associated to a specific maintenance operations so that we can compare between different maintenance strategies, taking into account the total cost and efficiency of each strategy. Achieving the desired objectives, we developed a holistic approach that starts by defining risk scenarios by collecting required data regarding the torrent, then identifying hazard scenarios by creating fictive series of flood events with defined dates and peak discharges occurring over a considered lifetime period, and finally by analyzing the possible consequences of these flood events. In fact, these events trigger bed erosion and material deposition. Thus, the dimension of scoring under the foundation of the dam depends on the bed variation and on the intensity of the flood. Finally, due to the removal of materials under the foundation of the dam, these stresses will be redistributed on the soil, thus triggering loss in external stability of the dam. Move to the physics-based modeling, in which we first start by analyzing the response of the global torrent bed using a hydraulic software called LogiChar. Simulations via LogiChar result in the evolution of the torrent's bed level after each event involved within the series of events. We then estimate the dimensions of the local scoring based on existing approaches, And taking into consideration the redistribution of stresses on the soil caused by scoring, we can verify the external stability of the dam against soil rupture or the exceedance of bearing capacity, against overturning of the dam, and against the sliding of the dam. And then, in order to define a global degradation state of the dam, a degradation indicator that incorporates all the possible considered stability failures should be defined. So we define SG, the global stability indicator, as a combination of the three normalized stability ratios related to the external stability, the bearing capacity stability ratio, the overturning stability ratio, and the sliding stability ratio, where SG, the resultant, is a non-dimensional global stability indicator that ranges between 0 and 1, where 0 corresponds to failure and 1 corresponds to maximum stability level. Based on the evolution of this indicator, we identify thresholds in order to create intervals corresponding to different states of the system. In this study, we define 4 different states: good, poor, very poor, and failed states. Finally, using the evolution of the global stability indicator, transition times between the defined states can be estimated. However, since these transitions are stochastic, several flood series scenarios must be generated and simulated in order to fit a probability distribution for the stochastic transitions to be then used in the final modeling, which is the development of a reliability-based model using stochastic Petronap tools. These models aim at representing the change of state of the structure over their lifetime periods based on transition between these states when the structures are exposed to deterioration mechanisms or to maintenance strategies. So, the first step will be to construct the Petronap model, which involves 3 processes: the degradation process, where we have the 4 defined states represented by P1 to P4, and the stochastic transitions between the states. Then, we have the inspection process, necessary for detecting the state of the dam, and finally, we have the maintenance process, in which each state is associated to a specific maintenance operation. So we consider if the dam is in a good state, no maintenance is required. If it's in a poor state, minor preventive maintenance is required. If the dam is in a very poor state, major preventive maintenance is required. And if the dam completely fails, corrective maintenance is required, in which the dam is replaced by a new one. 4 maintenance strategies are then defined to be compared. So in the first strategy, we allow all maintenance operations to be applied. In strategy 2, we inhibit minor maintenance. In strategy 3, we inhibit major maintenance. And in strategy 4, we only allow corrective maintenance, in which we allow the dam to deteriorate until reaching a failed state without any prior preventive maintenance. And then, after its failure, we replace it by a new one. After Monte Carlo simulation, the outputs will be the time spent by the system in each state and the number of maintenance operations carried out over the duration of simulation. These results help in choosing the best strategy to maintain the system, taking into consideration the total cost of each strategy and the availability time of the dam in non-critical states. We applied the developed methodology on a check dam located in the Manival torrent in France. Most of the data required for the simulations and calculations were extracted from the ONF RTM database. Regarding the flood scenarios, 50 flood series were generated. All events are considered to be clear water floods. Only floods with a return period of 10 years are considered, and the modeling is performed over a period of 100 years. Regarding the physical modeling, this is an example of flood event series corresponding to the first scenario generated in the scenario. In this scenario, 8 flood events occurred over the 100 years. This figure is the output of the simulation of the first scenario via Logichar. It reveals how the bed evolves upstream and downstream the check dam to be modeled. After the evolutions of scoring and stability indicators were obtained, the combination of these stability indicators are proposed before results in the evolution of the global stability index over time. So, this figure reveals the evolution of the global stability of the dam for 5 of the generated scenarios. After calculating the time spent in each state in all the scenarios, permits us to estimate the empirical cumulative distribution function for these stochastic transitions as shown in this figure. The resulting transition laws were then used as an input to the developed SPM which is applied on the check dam under study. This table reveals the influence of each maintenance strategy on the mean sojourn time in the 4 defined states. Also, the statistics on the number of applied maintenance operations allow us to compute the total expected cost of each maintenance strategy as shown in this histogram. The results obtained reveals that for check dam under study, strategy 3 is the cheapest. This can be interpreted by the fact that the system is not allowed to deteriorate to states where expensive maintenance operations are required, and it is directly repaired by minor operations which are less expensive than major ones. In this study, we built transition laws between the states of the dam by analyzing the time-dependent evolution of the defined degradation indicator, moving from multi-scale physical and analytical hydraulic models to external stability analysis of the structure. We then used this physics-based information to provide a stochastic model for the evolution of the dam stability using Petronap tools that permits us to assess the efficiency of preventive maintenance strategies to be applied to the dam. Such work can be developed further by considering more failure scenarios, also by taking into account the effect of information imperfection resulting from uncertain, imprecise, or incomplete data by using or doing sensitivity analysis. Finally, by studying interactions between check dams constructed in series, so to know how the presence or the absence of one dam can affect the behavior of other consecutive dams. Thank you.